Okay, so I'm going to talk a little bit about the software platform for HEAP, because HopsWorks is not a hardware platform. We have CSC in the project who are providing compute resources, storage resources, GPU resources for the project. So it's a software platform. And it's a software platform for developing programs, for running those programs or operating them, for storing data, for sharing data, for collaborating and working together. And in the whole area of exposome, we have many different types of data. So you'll have sequence data from sequence machines, you'll have consumer data, which will be in a tabular format, so in databases. You may have image data, you'll have sensor data, and all these different data sources we want to bring to a single place. And that's what HopsWorks is. It's a platform for also scalable storage of data, very large volumes. So I'll give an example of a workflow that we did with Karolinska, which is where the Joachim has a petabyte cluster. So petabyte, for those of you who don't know, is 1,000 terabytes. So the platform was originally designed, actually in a new project many years ago called Biobank Cloud, with the strong security requirements that we have in medical research in particular. So in medical research, we often, when we're working on some data and we want to put that data into a shared cluster, we want to limit who can access the data. We still want to run programs in that shared cluster. We want to utilize the resources in the shared cluster, but there's often security challenges to making sure that data in a shared cluster, which is sensitive, can be kept sensitive, and that the people who process it can't cross-link it with other data or copy the data to somewhere else. So the platform has quite unique technology in that space. We have something called a project, and once you're inside a project, you can't copy data to other projects, you can't even read from the other projects. But I won't go into too much details on that. But as a platform, it's designed for storing all of these data types. So you can have files, you can have tabular data, image data, so on. Biological and medical data, we can call it in the middle. And I'll just talk a little bit about some of the things you can do when your data is there. So firstly, I mentioned security and storage, so we can scale to huge volumes of data. Right now in HEAP, we don't have those huge volumes of data, so we're hoping that we'll see more of that data later in the project. There's been quite a lot of work from Graz and KI in curating the data, so being able to design metadata to find your data and to organize your data. Joachim mentioned earlier the challenges related to sharing data across these medical research boundaries, so there is great support for collaboration. You can have teams of people in your project. So if you're familiar with, if you've ever programmed and worked with something like GitHub, it's kind of like GitHub repositories where you can have many people sharing and working together. And then finally, analyze and predict. I'll talk a little bit about what you can do as a programmer. So this is not a platform where you're going to point and click and do things. Unfortunately, it does require a certain level of computational skills, and primarily I mean programming skills. But we'll get into that in a second. So just to give you an idea of what you can do. So why is this a little bit different to running with your laptop or a server that you have in the office? This is an example of a pipeline developed by, in collaboration with KI and HopsWorks. It's on the human papillomavirus. It's a meta pipeline for identifying HPV transcriptions. And it took 100 terabytes of the TGCA data, so it's quite a large data set, and there's 10,000 BAM files in it. And it's basically then taking that data, and it's using SAM tools that many of you will be familiar with if you've worked in bioinformatics, to remove all of the low quality human reads in there, and we get then a bunch of FASTQ files. Sorry, I'm going to go back. How do I go back? We go there. And then it's removing the human reads, and we get to 20 terabytes, and then we go back to SAMQ tools, and then we use Diamond to do some protein alignment. But the main point here is that you can see there are very large volumes of data, and really in the space of Human Exposome project, when we have sensor data coming in, when we've got sequence data, many data types will be of this size and order of volume, and that is quite intimidating to a lot of people who maybe have just taken a Python programming course at university or after university. So if we look at the top of the screen, you can see that it says something called Jupyter Notebook at the top. This particular pipeline is written in Python code in a Jupyter Notebook. It's actually a few different Jupyter Notebooks. And those Jupyter notebooks run Python in a framework called Spark, which enables us to run at this huge scale. So you need many machines to make this work in a relatively reasonable amount of time. And then we can automate, or what we call operating, with something called Airflow. So we can automate this process. Because ultimately, if you want to do something, build a prediction service of value. So if you're doing research and you have a data set and you produce an output, that's fantastic. But if you're building something that's going to move in and actually maybe work in a clinical setting, then it needs to keep doing it. New data will come in, you need to reprocess the new data, you need to then produce the output. So Airflow is a tool that helps you do this, and then we have a file system underneath it all to manage all those huge data volumes. So I mentioned that this is primarily a platform for people who like or can program, or somewhat programmer literate. So if you're familiar with Python, you don't have to, in a lot of people who do courses nowadays and want to do some Python programming, immediately they'll find out about something called Docker, and now you're writing Docker files, and now you're having to learn how to install all these packages. It's much easier than that on our platform. You just have to search for the packages you need. We use something called Conda to manage your Python packages. You don't have to write Docker files. Underneath it, there is support for GitHub now in the platform, so you can manage your source code in GitHub, you can run notebooks in the platform, and there is Spark support for that scale. Now, a lot of people are working with machine learning. A lot of people are talking, probably all of you in all of your proposals have some AI element in it, I expect. And the platform really supports pretty much any modern ML framework that you want to use. Some of them you might need to install, but many of them come built in. And there is support for GPUs, I should mention as well. And I think there's one GPU currently, and hopefully there'll be more later in the project. So another thing that the platform does, I mentioned already, is this support for what we can call research projects, where you have your own private project. You can see on the left-hand side we have Institute A researchers are inside this project, and maybe the project is related to cancer and they have a lot of data related to cancer. Maybe you're doing AI and they have models. And then there's another Institute B who have a number of researchers who have access to their data set on nutrition, and there's possibility in the platform to share data. It's really just a couple of clicks. So you have to approve, you have to search, but it really removes all barriers to sharing between research groups, right? Now you can no longer claim that it's difficult to copy the data here or there or so on. It's really just a trivial way of doing that. So, you know, if you talk about sharing and managing your data, and Eva talked a bit about the legal challenges of managing large volumes of data, there is a lot of capabilities in the platform for ensuring that your data is not just secure, but you can see who has done what. We call that audit trails. You can decide who can access the data in what way, so we call that role-based access control. So you can say, well, this person is allowed to process the data in programs, but they're not allowed to update this data set. So we have two different roles for that. One is a data owner, from a GDR perspective, who's responsible for the data, who's allowed to join the project. And then a data scientist is the person who can then run the programs, but not update the data or manage membership of the project. We're doing some work we're doing quite a lot of work in the project related to how we design metadata for the exposome. So we have developed a technology that we call schematized tags. So this is data about data. That's what metadata is. So if you have some sequence data and you want to know who the type of machine that was used to sequence the data, the origin of the data, you want to know the person who created the data, excuse me, we can manage all of that in metadata or schematized tags. Excuse me. And there's great support for search then. When you annotate your data with metadata, you can use free text search to find things. Okay, so I mentioned before that operationalization is the kind of next phase after research. And this is just to give you an idea of what you would do when you're operationalizing a machine learning application. But I'll give you the main motivation for operationalization in AI is that if you train a model in AI, so imagine we have a system for screening for cervical cancer, and that's our online service in the top left. And every week there's going to be new samples arrive, okay? So new samples will arrive. We'll want to sequence them, we'll want to then extract the data, and we'll want to then use a machine learning model potentially to predict for something in those samples. Maybe we're going to do all of the other big data steps of processing the raw sequence data, to identify HPV transcriptions and so on. But there's a bunch of different things we can do. The point here is that this is what we call a flywheel, that the more data that arrives in, the better the predictions you get, because you get better models, which means that you get better service, which increases people's confidence in the platform, which means that more people will add more data. And we can call that a data for AI flywheel, that the more data you add, the better it gets, and the thing just keeps getting better and better. And just to tell you an anecdote on this, I read a story about a normal computer programmer in China who built a system for identifying breast cancer in mammogram images. And what he did was he built this system. He got a data set from Barcelona with annotated mammogram data, and he built this machine learning system to predict if you uploaded your own mammogram images. So people started doing it in China, and they kept doing it, so the system kept getting better, because people didn't just upload it, they also said, well, here's the annotation for where the tumor was in the image. And right now, this is incredibly popular in China. People are uploading their own data privately, and it's getting better and better. The more data that gets uploaded, the better it gets, which means more people get interested, which means it's now, it's now become your doctor that gives you a secondary diagnosis, or if you need a second opinion on your mammogram images, that people go to that system. He's using it also for brain tumors as well. So operationalization is built into the platform, and if you can get us a workflow together, we can help you turn it into something which really becomes a service, a prediction service that you can advertise to people. Now, I'll just say a couple of little technical things that we've been doing on the platform. This is a big platform. We're a company of 40 people, and we sell the platform as well. It's an open source platform, so all the stuff we do gets fed back in. But some of the kind of things that we've been doing are, people want general purpose compute, so we've added that support with Docker images. So if you're writing programs in Python or in C++ or in Fortran, you can run them now. And we've added a lot of new support for metadata. We've rewritten the system completely. And with CSC, we're working on, they have this air-gapped environment where the most sensitive data can be stored, called ePowder. And we're installing the platform there, and we already have support. It's already running on CPowder, which is, you can access CPowder from outside the system direct. And of course, we're here as a company also to help you if you have challenges related to working with large volumes of data and how to get started. That's one of our roles in the platform. So with that, I'll finish. Thank you.